This is the AP Physics workbook. This is problem K in Unit 3. So you've got here, we want to measure the coefficient of static friction between a coin and a steel plate. The student attaches the plate to a freely rotating axis so it can go round and around. For each trial, the student sets the coin at different positions on the plate and measures this distance r. So it might be here, 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 right? The student also has a stopwatch that measures period t of the rotation. So from a top view, if you were looking down on it, let's say the object was here. So here's mass m, and again, here's r. Here's the axis of rotation right here, and this is rotating this way, right? So the number of seconds per rotation is this period t, right? So that can be measured as well. How can you use this setup to take measurements that would allow the coefficient of friction to be calculated? Be sure to explain what rotational period must be measured and how experimental error could be reduced. So this is not a lot of space, but I actually find it a little easier to derive the equation first and then come back to do that. So that's what I'm going to do here. So net force on circular motion, right? Centripetal force. And so I need a free body diagram. Here's the object from a top view, from this view, and I've got here friction force. From a side view, if I look at the coin from this point of view, I'm going to have normal and weight and friction force. Where this is my line of action. This is a better free body diagram because you can see all the forces acting on it. If you only draw this one, it's really going to limit you. So this is your top view, but not so useful. So you don't have to draw this one at all. It's whatever you think of first. So this is friction equals mvt squared over r. Friction is normal times coefficient of friction. And I know that on the y-axis, Fn minus mg equals 0, so Fn equals mg. Let's plug this in. And then we can plug this in. Now, this chart here is meant for you to write down what I'm saying out loud. So I'm not going to take the time to do that because I don't want to make a video that's like 20 minutes long here, but that's something that you can that you should be practicing doing, like what's your rationale for each step. And we're still not done because we've got mu, we've got r, but we don't have the period in here anymore. So where does period come into play? Well, the period is related to the velocity. 2 pi r over the period is velocity. So now I'm going to substitute that in. Umg equals m and then 2 pi r over period squared over r. So mass is gone. This squared is going to be 4 pi r squared over t squared. And now divide by r, it's going to cancel one of those. So mu times g equals 4 pi r over t squared. Now we derived this, I forget what problem, we derived this in another problem as well, or they derived it, I can't remember. And we talked about this in a similar context, a turntable one. I don't know if it was F or G or what, but something similar. This has only the things that they mentioned, mu, r, period, all fundamental constants, 4 pi, g, those are all allowed. Okay, so now that I see this, I go, well, how can I calculate the coefficient of static friction? Well, in order to do that, I need to measure r and I need to measure the period. Everything else is known. So I'm going to say here, place coin on plate and measure r from center. I really should use their symbol, r. Turning the motor on. measure the period. At which the coin slides off. Okay, so what you want to do is you want to find that maximum value, right? As you increase the rotation, right, there's going to be some limit to when, like how fast you can go before it slips. So you want to repeat 3 times and take the average. You can also say to repeat that for different radii and different periods. Okay. So here's the data. The student collects the data shown in the table above. Well, it's right here. Plot the data on this graph. So they actually made the graph for you. We just have to plot it. So we're doing the radius versus period squared. So we've got 0.1 and 0.96, 0.2 and 4. God, this is small. 0.3 and 5.3, 0.4 and 7.3, and 0.5 and 8.4. And it makes more or less a straight line. So let's not perfect because it's an experiment. So we're going to have to use the slope of the best fit line and the equation from part B. So part B we got, I'm just going to rewrite it. Now you don't want to just plug in a data point. We're going to use the slope. So when you look at this here, you're going to write y equals mx. We're going to assume that, right, when there's no radius, you can't measure the period, so we don't need the plus b part. So if we find the slope, we'll do that the same way we did the previous problem. Let's find 2 points that are nice. Well, we're going to do 0, 0, and we can do this point here. Remember, don't use data points. Like I could have used this one because it's right on my line, but be very cautious about that. Make sure it's on your trend line because they do check. And as long as you show your work, you can't really lose you can't lose points. Not easily anyway. So if this is the generic equation of the line, now we've just gotten the slope, so this makes it y equals 17.5x. Well, according to this, it's t squared equals 17.5 times the radius. So if I rearrange this equation to fit this format, this is the theory, then I would get t squared equals 4 pi r over mu g. So this theoretical equation has t squared and r. That means that everything else is the slope, this part. So 4 pi mu over mu g equals 17.5. And I know this is 4 pi over 9.8 times 17.5 is going to be mu. So I'm rearranging it because I have to solve for mu. So let's do that. So 4 times pi divided by 9.8 times 17.5. And I got 0.073.